Hello everyone, welcome to this video tutorial on how to solve the differential equations using Laplace transforms. This is the differential equation we are going to solve. We are going to plot this solution in this video. So the learning outcome of this video is that after this video lecture you will be able to solve differential equations using Laplace and inverse Laplace transforms in MATLAB. So in the last video only we have seen that what is the Laplace transform. Actually it is an integral transform that converts a time domain function, mathematical function, to a complex variable function, that is S, which is also called as a complex value frequency domain or S domain or S plane. So this is the general function f of how the general function f of t is converted to f of s, the function of s, that is a frequency domain parameter. Where s is a frequency domain parameter. Now in this video we are going to convert or solve this differential equation, which is the differentiation of a time domain function, differentiation of a time domain function. So the steps are like that. As we know that y of t is the solution of this differential equation. Y of t is solution of this differential equation. So to solve this differential equation or to obtain y of t, what we have to do, we have to convert this differential equation into a form of Laplace transform of y of t. Using this iterative procedure, we will see how to do this in MATLAB. So the first of all, we have to convert this differential equation in the form of Laplace transform of y of t, that is frequency domain. Okay, and whenever we do an inverse Laplace, as we have seen in last video also, inverse Laplace will convert that frequency domain function to the time domain function. So let's move to the MATLAB. We have to solve this thing, so we'll start with the CLC and clear all. We'll run this once again to see that our workspace is free. Here, so you can see here our workspace is free. Then we'll move forward to define the symbolic variables. Define the symbolic variables. Okay, syms is the function we have to, or keyword we have to type to define the symbolic variables. Then we'll define first symbolic variable as y of t here, then t and s. Okay, so after that what we have to do, we have to define the variables to store this differentiations. So define the variables to store differentiations. differentiations. Okay, so I will create a variable d2y, which is nothing but a diff. Diff is the function to define the to do the differentiation actually. So we have to do the differentiation of y of t, okay, with respect to t, once again with respect to t. So this means that double derivative of y of t function. So this means that y of t with to t. Similarly, we'll create a dy, is nothing but the differentiation of y of t with respect to t. Okay, so this means that first derivative of y of t with respect to t. Okay, I'll write 2. Yeah. So this is how we can write. Now we will write the differential equation. Okay, differential equation is nothing but dy d2y, that is double derivative of y with respect to t, plus 2 star, that is twice 2 multiplied by dy, that is a single derivative of y of t with respect to t. Okay, plus now here we have to be careful, we have to write y of t. This y of t is nothing but the f of t we have used previously in last video, that is similar, that is the function of t. Okay, now is equal to exponential minus t. Okay, so this is the differential equation we are going to solve. EQU8 okay. Now we'll run it once again. Yeah, here we have to use double equal to use it as a differential equation. So we have this differential equation, you can see, which is similar to this one. Okay, yeah. So the next thing is that as has told you before, we have to convert this equation into frequency domain equation. Okay, now to do that we have to write convert this differential equation to frequency domain equation. Okay, now how to do that? We just have to take the Laplace transform. So function Laplace, I'll write this as a function Laplace is equal to Laplace. Okay, then we have to use this differential equation comma t comma s. Okay, so if I'll run this thing, yeah, you got this. So if we convert this differential equation to the Laplace, you got this thing. Okay, so I forgot one thing, that we to define these initial conditions, I'll write this initial conditions here. Initial conditions. Okay, so y of 0 at time t is equal to 0, the value of y is equal to 0, and this dy by dt, this is dt. Now this is image, I cannot change it, but this is dy by dt, sorry for that thing. Okay, now dy of 0 divided by dt is equal to, so that is first derivative of t with respect of y with respect to t at time t is equal to 0 is 1. Okay, so these are the initial conditions. Now we can see here we have this 2s Laplace y of t ts. Now what we have to do, we have to do that thing, we have to take this Laplace y of ts as a common. So first of all, what we'll do, we'll substitute the initial condition. So y of 0 is nothing but the 0, and this d by dt into y of t at t is equal to 0 is nothing but 1. So how to substitute these initial conditions? Substitute the initial condition. To substitute these initial conditions, there is one function I'll use flap again because we are not going to change the equation, that is the same equation. Yes, capital F underscore lap, enter is equal to, now we have to substitute, the function is subs, where we have to substitute in flap only, okay, or after initial condition I'll write initial condition 1, okay, and where we have to substitute that thing in flap, okay. What we have to substitute, y of 0 with respect to or with we have to substitute the value is 0, okay. Now we'll run this once again and we'll see. You can see here we have 2 into y of 0 that has been eliminated from this equation, okay. Here also s into y of 0 has been eliminated from this equation, okay. So that means that it has multiplied that s with a 0 or 2 with a 0, okay. Now the next substitution is, I'll copy this thing, I'll write this first initial condition, I'll write a second initial condition here, second initial condition. So what was our second initial condition? So we have to substitute in this first equation with dy is equal to 1. dy is nothing but, here is our first differentiation with respect to t, and we have to substitute its value is equal to 1. So this will become 1 now, okay. So we'll run this once again. Now here we have f after Laplace after substituting two initial conditions, okay, and this is 2s Laplace yt of ts, then s square Laplace f square Laplace. Now from this equation we just have to take this Laplace y of t common, and we have to shift the other terms to the another side of equal to sign. But before doing to that thing, this equation cannot be used, okay. So what I mean to say that we have to substitute something in place of this, because we are going to use this function solve. What we have to solve, we have to solve this thing to rearrange the terms. Yes, as we have to rearrange the term, and we have to take this Laplace y of t of s t comma s common, and we have to shift other terms to the other side. We can use this solve, and what we have to solve for this, we have to solve for this. But if we'll run this, it will give an error. You can see warning, unable to find explicit solution. So to perform this solution, or to segregate Laplace y of t s, what we have to do, we have to substitute some variable here. Now replace, I will say replace okay, not this, control C, replace Laplace with some or I will say alphabet or variable or anything. And now what I will do, symbolic variable again, s5ms, I will define that symbolic variable as y of t or yt, okay, small yt. Now what we have to do, we have to substitute this going to replace with this. What we have to change, we have to replace this Laplace whole thing with respect to yt. Okay, yes, that's the problem. Now in this equation, replace this whole term with yt. Okay, and we already defined this symbolic variable yt. Okay, now what to name this? We have to name this something final lap after replacement, or I will change final lap, so final Laplace equation. Okay, so final Laplace equation, and I will delete this thing and I will run. So yes, we got this final Laplace equation. So what is the equation? You can see here, this Laplace y of t of t comma s has been replaced with y of t. So this s square yt, this is 2yts, 2yts and 2yt minus 1 equal to 1 plus s. Now just take this yt common, we'll get the solution in the frequency domain. So solution in frequency domain is equal to solve. Now what we have to solve? We have to solve this final lap, and we have to solve it for yt. Shuffle the terms. So shuffle the terms in final lap to get the final frequency domain solution. So to do this thing, we are going to use this solve function for y of t. Okay, and just do this thing. So this is the solution in solution in frequency domain. So what it did, it just took this yt common. So what is remaining from first of all, it shifted this minus 1 to add this 1 with 1 upon s plus 1. So this numerator we have obtained. Then just take yt common, so remaining terms are s square plus 2s plus 2t, there is no t, so this will become the denominator here. So this is our frequency domain solution. Now to obtain, take the inverse Laplace, or perform inverse Laplace operation. Inverse Laplace operation on the frequency domain solution. Domain solution. Okay, so how to do that thing? Y of t. Now I will write this function as a y of t. Okay, y of t is nothing but the solution is equal to inverse Laplace. Take this inverse Laplace of what? Solution in the frequency domain. Okay, and we have to convert s to t. Okay, and what we'll do, first we'll see the solution. Yes, this is the solution we have got. Now if you have to cross check this once again, we'll first plot this is using easy plot function. Create a plot of this y of t, and this interval is 0 to let's say 3 or 4. Okay, fine. You can see here we have obtained the solution for time is equal to 0 to 3 seconds. Okay, so this is y of t, function of t, and here we got the solution. Now if you have to cross check this, you can directly solve this differential equations. Solution to differential equation using dsolve. So dsolve, this is the function used to solve these differential equations. Now you can cross check this solution. So we have, using this direct method, we have got the solution e to the power minus t plus c1 e to the power minus t cos t minus c2 e to the power cos t. So if you substitute this initial condition that y of 0 is equal to 0, we will get one constant, and d of t second initial, if you substitute this second initial condition, we will get the second constant. So thanks for watching this video. Please like, share and subscribe to the channel. Thank you.